When we first began talking about integration, we were interested in solving the area problem, which is, as we stated it at the time, was to find the area under the graph of some continuous function f on some interval closed AB. And the way we approached it was, of course, to slice the interval into a number of subintervals of equal width and make areas of rectangles that fairly closely correspond to the area under the curve on the subintervals and add them up. And at the time, we could have broken in one of two directions. We could have gone in a very hardcore numerical direction and began to look at how we could just crunch these things down by means of gadgets into smaller and smaller intervals and add up the actual areas of some rectangles. The direction we chose was to look at taking a limit and defining a definite interval. But we want to go back to these ideas from the very beginning about chopping up into subintervals as a way of getting approximations in situations where you don't know how to get an antiderivative, so the fundamental theorem isn't available to you, or you don't feel like doing the work. So we're going to start by reviewing some things that have to do with Riemann sums. And I've got here the graph of some function f on closed AB, chopped it into a number of subintervals of equal width. So we start at A, which we can label x naught, and then the partition is x1, x2, and so on up to x sub n, which is equal to b. And then we can take a look at the generic kth subinterval and pull it out and blow it up and remind ourselves of how a bunch of the labeling went. The width, of course, if this partition is regular, of each of the subintervals is delta x equal to b minus a over n. And so at the left endpoint, you would have x sub of the kth subinterval. You have x sub k minus 1. At the right endpoint, you would have x sub k. And at the midpoint, you would have the mean of those two values. It turns out x sub k minus 1 is whatever your a is plus k minus 1 of these delta x's. At the right endpoint, x sub k is a plus 1 more of them, because you're one delta x farther along than you were. And at the midpoint, you are a plus k minus a half delta x, because you are midway between x sub k minus 1 and x sub k. And then you can plug each of these into the function, and you can get f of those various x's. And then for convenience, you can take f of x sub k minus 1 and just call it y sub k minus 1. You can take f of x sub k and just call it y sub k. And you can take f of this average and just call it y sub m sub k for the kth midpoint. We're going to start by taking a look at left endpoints, just as a refresher, and we'll go through the right endpoints and the midpoints as well. So each of our rectangles, if I use left endpoints and I have n subintervals, then each of our rectangles is going to be the delta x times the height. So let's just factor out the delta x, and the delta x is b minus a over n. And then what we have left over are the heights. And what are the heights? Well, they are, since it's left endpoints, f of x naught plus f of x1 plus f of x2, and so on out to the last of the left endpoints. And that gives us f of x sub n minus 1. And we could, for the sake of convenience of expression, rewrite these things as y naught plus y1 plus y2, and so on to y sub n minus 1. Not so tough. And so in the case of my picture here, this would be the left endpoint estimate. And as we'll recall, left endpoints are going to give an underestimate where the function is increasing, and overestimate where the function is decreasing. Right endpoints, very similar in spirit. Right endpoints are going to give an overestimate for an increasing function, an underestimate for a decreasing function. A right endpoint estimate with n subintervals is going to have, of course, a bunch of rectangles that also have this width, b minus a over n. But now the heights are all given by right endpoints, and things don't differ by much. But instead of starting with f of x naught, we start with f of x1, and then f of x2, and so on, all the way out to f of x sub n minus 1. And then finally f of x sub n, because although it was not a left endpoint, x sub n is a right endpoint. And we can then, if we so desire, re-express this as well by calling these y sub 1 and y sub 2 and so on to y sub n minus 1 and then y sub n. So far, nothing new, nothing difficult, nothing extraordinary in any way. Let's take a look at midpoints. In terms of my picture, the midpoint estimate would be here. I would get it by plugging in the midpoint value of x to the function. These are still going to have all of these subintervals widths b minus a over n, and so we can factor that out as we did in the other cases. And then what have we got? We've got f evaluated at these sort of midpointy locations. So we will have f of x naught plus x1 all over 2 plus f of x1 plus x2 all over 2, and so on, all the way out to f of x sub n minus 1 plus x sub n all over 2. So we're splitting the difference between the left endpoint and the right endpoint on each subinterval by taking a mean, and then we're plugging into the function. And if we want to make our lives a little bit easier notationally, we can just call these y for the first midpoint, y for the second midpoint, y for the third midpoint, and so on out to y for the nth midpoint. Another way you can imagine making an approximation is to do something like this. You have your usual labeling scheme, you've got your function, we'll just look at a single subinterval. So here's the kth subinterval. And what you can do is you can locate the midpoint of the subinterval, find the point on the graph of the function that corresponds to that, and you can imagine making a tangent, assuming it's differentiable there, you can imagine making a tangent to the function at that point. And that tangent line on this interval would be the top of a trapezoid, where we've got a trapezoid height here and the two base lengths of the trapezoid here, and we could bust out a little geometry and figure out the area of that trapezoid in principle, although in practice it would be pretty ugly, right? Because we would have to figure out the equation of this tangent line, we would have to figure out where this tangent line intersected these two vertical lines, and it would get to be a whole thing. But fortunately, there is an observation that we can make. Let's do the plain old midpoint approximation. So I'll do the rectangle top in classic Riemann style, and let's take a look at these two triangles that represent the difference between the tangent line estimate and the midpoint estimate. And it should be fairly readily apparent that these triangles are congruent. They both are right triangles because we're working at the midpoint of the subinterval. These things are equal. We've got some vertical angles here that are equal. And so by angle side angle, the triangles are congruent, which means, interestingly enough, that the two estimates yield the same result. So I can take a plain old midpoint approximation, or I can take this possibly fancier approximation where we take a tangent to the curve at the midpoint of the subinterval. And because of the congruence of these two triangles, it turns out that they yield the same value. So you'll occasionally hear the terms tangent line approximation and midpoint approximation used interchangeably. And it's good to remember that anything that you can establish that is to be true about a tangent line approximation has got to be true of a midpoint approximation, and vice versa, because although they come from a different place conceptually, they yield the same result all the time on each subinterval. We're now going to take a look at a thing that is not a Riemann sum because it's not based on or equivalent to a rectangle, and it's what's called a trapezoid estimate. Not the same trapezoid that we saw a moment ago that comes from the tangent line approximation, but a somewhat different one. It's the one that gets the name trapezoid approximation. And the way that works is we take the point where the graph of the function intersects the left edge of the subinterval, the point where the graph of the function intersects the right edge of the subinterval, and we just connect them by means of a line. All right, so this is the thing that we'll call a trapezoid estimate. The hope might be that the trapezoid estimate would perform a little more accurately or precisely than any of the Riemann estimates, because it gets to slant. It gets to at least follow the increasing or the decreasing character of the function, and perhaps that in the end allows us to have a better estimate. So the first thing we need to do is sort of bust out some information from geometry and ask ourselves, well, what is the area of this trapezoid? And in the general case, the area of a trapezoid is half the sum of its bases times its height. And so what is that in these terms? Well, it's half of, let's see, it's not about orientation, remember, right? It's about what's parallel. So the bases of this trapezoid are the left and right edges of the subinterval, and so they are going to be f of x sub k minus 1 and f of x sub k, respectively. And then the height is the distance between those parallel bases, and that's just going to be our delta x, or in terms of the original a, b, and n, it's going to be b minus a over n. So then what if we add a bunch of these things together? We might call this T sub n, a trapezoid estimate with n subintervals. And what's it going to look like? Well, so the first one is going to be half of, let's factor out all the b minus a over n's, right? So it's going to be half of b minus a over n times what? Well, so on our first subinterval, we're going to have f of x naught and f of x1, right? And I'm going to run out of room, so I'll go down here. And this distribution here still applies, right? So then we're going to have, on the next trapezoid, f of x1 plus f of x2, and then we're going to have f of x2 plus f of x3, and so on, out to finally f of x sub n minus 1 and f of x sub n. And you notice we have some opportunities to combine things, right? Because except for the very first x naught and the very last x sub n, everything appears twice. Once at one edge of one trapezoid, and again at the right edge of another. So this is going to be, if I combine a little bit here, b minus a all over 2n times f of x naught plus 2 f of x1 plus 2 f of x2, and so on. 2 of everything out to x sub n minus 1, and then finally f of x sub n. And if we wanted to use a little more convenient notation, we would say b minus a over 2n times y naught plus 2y1 plus 2y2, and so on, out to 2y sub n minus 1, and then finally y sub n. So the actual calculation is not so bad. If you have these function values, you just have b minus a over 2n on the outside. You've got all the function values, all but the first and last, doubled. And so if you had a calculator that was set up to do this for you, it wouldn't be so terribly difficult. It turns out that the following thing is true, though, and that is that a trapezoid estimate for the same function, same interval, is an even-up average of the left and right endpoint sums. So although it's not itself a Riemann sum because it doesn't correspond to some sort of rectangle, it is in fact just the unweighted mean of the left endpoint and right endpoint estimate with the same number of subintervals.